There we are. Okay, so before we get into, just writing the formulas and solving the questions, I want to give you a little background of what's happening. So if you recall, in test two, there were two huge types of calculations that we did for significance. One was known as the usual range. And what we did, of course, was we took the population center and we added 2 standard deviations to it, subtracted 2 standard deviations to it, and said anything between here and here is usual. Anything between that lower and upper level is something we would expect to happen with normal variation. Anything outside of that would be unexpected, or in other words, significant. The other main method was our significance tests. Again, this is all from test two, in which case we found a probability of an extreme. And if that probability was less than 0.05, we would say, yes, it is significant. In other words, we would find either the area on the left of the curve or the area on the right of the curve, depending on which side of the center we're at, and determine how much area that is. Well, we've already done something analogous to the usual range. That should look very familiar to you. Essentially, what we've been doing now is we found the sample center. And instead of this arbitrary 2 standard deviations, we calculate something very precise called the margin of error. And we would add it in 2 different directions. In other words, add a positive and add a negative, or add and subtract the margin of error. And what we would say is between this lower measurement and upper measurement, somewhere between these values, anywhere in there, is the population center we're looking for, whether it's a mean or a proportion. And of course, this thing we've been doing was the confidence interval. And so essentially a confidence interval is essentially the same thing as the usual range, just for samples. And so then, of course, by analogy then, the significance is going to be the same thing as a hypothesis test. We're essentially going to find the probability of some extreme and find out, is it less than some number. But like before, where instead we're no longer using an arbitrary measurement, we made it more precise to this margin of error calculation, we're going to do the same thing. We're no longer going to necessarily say arbitrarily 0.05. It's now going to be some probabilistic value. We call it p-value for short. And is that p-value smaller than our significance, which we call alpha? And if the p-value is smaller than significance, then of course we call it significant. If it's not smaller, then we say it's not significant. And so when it is smaller, we use the word, instead of saying it's significant, we use the word reject the null hypothesis. And if the p-value is greater than alpha, our significance, then what we would say is fail to reject the null hypothesis. And so fundamentally, we're doing the same thing we've done before with the significance idea of finding the probability of an extreme. We're just now going to be more precise about what we call these two things. It's not going to be some arbitrary, just use any extreme we want and compare it to 0.05. We're going to have to dig through and figure out which kind of values to use. Because essentially the same concept, just now a lot more precisely calculated. And so when we're doing these kind of things, the first thing you have to fundamentally do before you can answer any of the question is you have to be able to identify the claim. And what do I mean by that? You have to decide, are we talking about proportions or are we talking about means? There's more than just these two, but for this class is the only two you need to worry about. Once you identify which one of these, you then have to decide, are we talking about a null hypothesis statement or an alternative statement? Luckily, these are very clearly defined. Null hypothesis must contain equality. That means if it's a statement that says equal to, if it's a statement that says more or equal, or less or equal, I am talking about the null hypothesis every single time. And you'll see some examples in a bit when we do this. Contrary then, the alternative statement cannot contain equality. So it can only have not equal to, less than, or greater than. And also notice that I put them in order on purpose. These two are considered opposites. These two are considered opposites. And of course, the last two are considered opposites. And so often you'll see us pair them that way. Technically, for the null hypothesis, we always just usually write this part here as the formula, and you'll see what I mean when we get there. And the bottom one here is what really matters. But sometimes, in some instructors, they'll make you pair them up appropriately. And so just to make sure if you're picking an inequality symbol, they go in the opposite directions. And so if I'm going less than, the other one is greater than, and so forth. So it just depends on how picky your teacher is. Most of the time, we'll use equality every time for the null hypothesis and not for the alternative. Why is that? Well, the second big thing, after you identify the claim, is we determine the test direction. Determine the test direction. That is, am I looking for the area on the left or the right? Well, we actually done this in the past without even thinking about it. When we're finding the probability that it's less than a number, we all know that meant that it would be on the left, right? We do norm.dis. I don't know why I added an E there. And then by contrary, if I found the probability that it's greater than a number, we would always find it on the right. Now we're just going to include one more. Find the probability. I see your note, Jax. That's fine. Yes. Not equal to a number. We call that two tails. So this is a left-tailed test, left-sided test, a right-tailed test, or a right-sided test, and then a two-tailed test because it's not equal to. The reason why this one is considered two tails is when you're simply saying not equal to, we don't know if you're talking about smaller or bigger. All we know is that it's not equal to. And so there's two possible ways it can go. And so whenever it's not equal to, it's two tails. And absolutely, y'all in the comments who want the old videos, I would be glad to send it to you. Going forward, just send me a private message and I'll be glad to just reply back that way. But I have you this time, don't worry. Now, one thing I want you to notice is what is telling me the direction. Oops, it zoomed in. What is telling me the direction? And I scroll the screen back. There we go. There it is. Notice it's just the pure inequalities. So that means the alternative is going to tell us which test to use, whether it's a left test, right test, or a two-tail test. And just so you know, HA or H1 are how we write the alternative statement. So you might see it either way depending on how your instructor likes to do it. Some do it interchangeably, but we either say HA or H1. HA for the alternative hypothesis, H1 to be like binary from H0, which is the null hypothesis. Either way you look at it, HA or H1 is going to tell us the test we're talking about. Once you determine your test, you're now ready to find the p-value, which again is just a probabilistic value, the p-value. And then once you have your p-value, you get to make a decision. And that decision, of course, is referring to this idea. Is your p-value smaller or is it bigger? And then once you make a decision, the final step and the part that gets most people tripped up is your conclusion. I hope today to show you a nice, easy way of interpreting that conclusion. If you don't like my way, that's fine. Just find a way that works for you. But we're going to ultimately make a conclusion about what we found in number 4. So this is the general 5 to 6 step process. Some people break apart an extra step in here, but it's the general 5-step process to doing a hypothesis test. Okay. And of course, I'll place this in the chat so you can have access to these things I wrote so far. One thing I want to bring to your attention also before I get into this, I want you to notice that we're introducing another standard error calculation. So for confidence intervals, our standard error was the square root of p hat times q hat divided by n. For null hypothesis, it's now going to be h naught times its complement 1 minus h naught divided by n. So why are we changing from p hat q hat divided by n? Well, a hypothesis test, the fundamental assumption about a hypothesis test is that we're assuming the null hypothesis is the center. We're assuming that this is the population center. And then what we're doing is going out to get empirical data to test whether or not this is the center. And the empirical data might be smaller or might be bigger. Let's assume for simplicity, it's over here and it's smaller. And so what we're going to find out is the probability of being this extreme so unlikely that we can confidently get rid of the null hypothesis and say it's wrong? Or is this probability rather large, in which case we can't get rid of it? And of course, what's considered small enough or large enough, that's back to the significance idea. Is that probability so small that it's so unlikely that we have to reject the null hypothesis? Or is it not? And so remember, standard error is always the amount of error we expect from the center. And so for confidence intervals, our center is the sample. But for hypothesis tests, our center is assumed to be the null hypothesis. And so we do standard error around that center. That's why we use a different one. Okay, enough of me setting the stage and blabbing on. Let's actually build our calculator that's going to do all these calculations for us. And again, you can find this formula on page 93. I just screenshot part of it so we're not overwhelmed with the information. I did add on a chart here that I feel will be very helpful in our interpretation. And then, of course, down here are some old formulas that we're going to recall and use to our advantage. Okay, so let's build the calculator now. As you recall, the yellow boxes are inputs and the white boxes are going to be formulas. So you'll see we have a few formulas we're going to need to add this time. And you're going to see me go a little over the top with how many formulas I'm going to write today, partly just so you can see the connections of everything. Going forward, when you do this on an exam, I anticipate you using a lot less formulas, as it might be a bit of overkill. But since it's your first time seeing it, I do want you to see how everything is connected and how everything builds off of it. So I'm going to intentionally go a bit over the top today. You can forgive me or hate me later, but I think it'll be to your benefit so you see how this all connects and not take any shortcuts. So the first thing, understand that we're talking about proportions, and so we already know that we're talking about P here. That is our center we're trying to find. And what usually happens is you'll write down some value, like 58% is your claim. And so we'd want the alternative statement to also contain that value. And so I'm just clicking E equals and typing D2 so that they show the same thing. So if this was 3/4, I would want the other one to say 3/4 and that kind of stuff. It is defaulting to percents. If you don't like percents, of course, you can change it to general and keep it as a decimal. It doesn't actually matter. I generally keep them as percents myself, but ultimately you just want these two numbers to match. And sometimes students don't realize that it should be the same number. So that's just a nice way to remind us that these two should always be the same number. Okay. And of course, I mentioned the null hypothesis. Usually we always write equals, but technically it can be equals and greater than or equals and less than. It doesn't matter because we always use the alternative to carry out the test. And so generally that box will always say equals. The one that really matters is this H1 box. It could be greater than, less than, or not equal to. And that will tell us the tail of the test. So what we're going to do is tell Excel to read that box for us. And we're going to do it by if statement. We're going to say equals if, capitalization doesn't matter, this cell is equal to the greater than symbol in quotes. Then we're going to say the word right. So we know those two are connected, and it'll be a right tail test. Comma, if, parentheses C3 is equal to, quotes, less than, then we want to say, in quotes, left. Otherwise, we're going to simply say 2, or 2 tails. Close my parentheses twice, and my formula is now ready. So C3 is greater than, that means right. If C3 is less than, that means left. Otherwise, assume 2 tails. That's what this code's telling us. So right now it says 2 because there's nothing there, but if I put greater than, notice it automatically tells me I'm doing a right tail test. If I put less than, it now says I'm doing a left tail test. So this tail is determined by the alternative statement. Doesn't matter what I write anywhere else, whatever I put here will tell me what tail I want. So it's reading that box. All right. Next major calculation is standard error. And again, that's that formula for null hypothesis, 1 minus null hypothesis divided by n. So equals the square root, the null hypothesis times, parentheses, 1 minus the null hypothesis, parentheses, divided by the sample size, the n, which is in cell B6. Close it, enter. And so if I knew this was like, 0.7, and if I had 30 people, I now have a standard error calculation. Okay, a test stat. That is simply a conditional z-score, which means a z-score based off the data. And we know how to get z-scores from data. That's just a standardize command. So we'll have standardize. The x is the actual observed value, which we know is p hat. In some countries, they call it p bar, so I listed that there too. But p hat. The mean is the assumed center, and that's our null hypothesis. And because this is a sample, we know we need to use standard error and not standard deviation. And so that's B7. So B5 was my p hat. B2 was my null hypothesis. B7 is standard error. Always your observed, your center, and how much error we would expect or deviation. And that will get you a z-score. And now we're ready for our probabilistic values, our p-values. We have a left, we have a right, and 2. And right here in these boxes, they tell you exactly how to calculate them. Norm.dis, 1 minus norm.dis, and then essentially double the smaller of the 2 calculations. Excuse me. So norm.dis of our sampled z-score, that test statistic, given 0, given 1, given true. And then we can do norm.dis, right tail, so 1 minus norm.dis of our test statistic, which is up there at, hold on, making that thing go away. Norm.dis, test statistic, given 0, given 1, given true. But I forgot my 1 minus again, didn't I? 1 minus, because it's a right tail. And there we go. And so what we want to do for the 2 tail is double the smaller one. And so what we want to do is have Excel look at these 2 calculations and decide which one is smaller for us. So we're not wasting our time or energy on that. And to do that, we can say equals minimum, and then this between these two values. What it's going to do is Excel is going to look at those two and decide which one is the smaller number. And then it's going to double it by timesing 2. So let's throw in some random numbers, make sure everything's working. 0.6, we'll say greater than. P hat might be like 0.55, 55, and we see a bunch of calculations. So we have the p-value from the left, p-value from the right, and notice it's picking the 22 and doubling it to get 44. And so we see everything going the way we want. The last thing we'll talk about is called type error. And for now, we're just going to program it, and I'll show you how to interpret that at the end when we get to some questions where it matters. So what we're going to do is understand your conclusion has two possibilities. You can either reject the null hypothesis or fail to reject the null hypothesis. So your conclusion could either be reject or fail to reject. So the two possibilities we can write in that box right there. So we want to read those options and then spit out the right kind of type of error. So equals if this box equals reject. It doesn't care about capitalization. We call that a type 1 error. So if you reject, the kind of error we would classify it as is type 1. Otherwise, if this box equals fail to reject, then we call it type 2. Otherwise, we're going to leave that box empty, which is why you put quotes with nothing inside it. So if it says reject, it's going to spit out type 1. If it says fail to reject, it's going to spit out type 2. Otherwise, it's going to show nothing. That's what that says. And so right now it says reject, so it says type 1. If I change it to fail to reject, it now says type 2. One thing to be careful about, if you misspell your word, it won't know what to do. So bear in mind that. It's reading the exact spelling of the words. Okay, so we now have a calculator built that will do a lot of the heavy lifting for us. It's a matter of interpreting. Remember, the first thing we're going to figure out is our claim. Then we'll figure out what kind of test to look for. And then we can worry about our conclusion. And this here will help us with the interpretation. The point of this calculator is to derive a p-value. If you already have the p-value in a question, you don't need this calculator. The whole purpose of this calculator, again, is to give us these 3 calculations. Sometimes they'll tell you the p-value is this, in which case don't waste your time on this calculator. You already have the calculations in front of you. You're ready to jump down to the last 2 steps here. Okay, take a look at the first question now. See if you could find the claim. If you've been using my strategies with reading these word problems, you'll know where to look always. You should always start at the very bottom. And so if you read that last sentence first, you already know what the claim is. It's very literal. The claim is proportion, so we'll say P is, which means equal to 1/4. We already got the claim out of the way. So that's the claim statement. Now we have to decide, is it the null hypothesis or the alternative? And you look right here. This is equal to. Which one is allowed to be equal to? The null hypothesis. And so we now know the claim, and we know the claim is the null hypothesis. So what's the alternative statement? If the claim is the null hypothesis, then what's the alternative of equal to? Well, simply not equal to. And that must be our H1 or HA. Now that we have all that, we're ready to import our calculator and do the calculation. We're going to come back here, highlight everything, make sure we get around the picture so it gets the picture too, copy, and then just simply paste. You'll see it comes with the picture too. Sometimes you got to remeasure and that kind of stuff. If you look carefully, you'll see that I had this column E a little wider than the other ones. That way it's already pre-fit. In reality, you would actually remeasure by double clicking the cells to fit and that kind of stuff. But let's fill in what we know. We know the claim was the null hypothesis. I'm going to put a little X next to the null hypothesis. We'll need that at the very end. We know the number in question was 1/4. So right equals 1/4. And we said the alternative statement is not equal to, because that's the opposite of equal to. So we're going to simply say not for not equal. And of course, not equal means that we want a two-tailed test. That means for the three p-values, I want to look at the p-value of a two-tailed test. I don't care about the other ones. They're not going to matter. I only need this one p-value at the bottom. That's why it's very important. The two-tailed means you want the two-tailed p-value. So let's plug in our numbers. We need to find our p-hat. And of course, looking above, we can see that we're looking at some kind of frequency of yellow. So how many yellows do we have? We have 158. And how many pods do we have? It's tempting to say 430, but if you read it carefully, you'll see it's not true. 430 is the green, 158 is the yellow. So in total, we got 158 plus 430 pods, because they're each individual colors. And so the total amount will be the total types of pods. So be very careful of those kind of questions. But we now know, just so we have it, 158 plus 430. This is a total sample size of 588. And we can say equals 158 divided by 588. And we now have our calculations. And again, because it's a two-tailed test, I only care about the two-tailed p-value, which is 0.29841. And of course, what was my significance level? They will tell you the significance level, or you assume 0.05. Here we can see they're telling us to use 0.05. So we're just going to write that in. And we want to compare our p-value, looking at just two decimals, is 0.29, and our alpha is 0.05. I hope we agree that the p-value is bigger than alpha. That means we're going to fail to reject. Remember, significance is when it's smaller. So we're going to fail to reject. So now we're ready for the hard part, the conclusion. But this table here should help you with that. So what did we do? We said the claim is the null hypothesis. And we said we're going to fail to reject. So we're going to look for where they're joined at. Draw a line through, draw a line through. This is your interpretation. So that represents what you would say. And the three dots here is when we insert two different things. The first set of dots is where you mention the significance level. The second set of dots is where you mention the claim. So in this case, there is not sufficient evidence at a 0.05 significance level to reject the claim, and our claim was that it was equal to a quarter. So there's not sufficient evidence at a 0.05 significance level to reject the claim that yellow pods are 1/4. So what are we saying when we say that? We're saying there's not enough evidence to say that's wrong. So we're saying that it seems like it's right. But we never say something is just right. We just can say that it's not wrong. Because we don't know. You get another sample, it may come contrary to that. But based on the current information, it seems like this number does make sense. And so that's what we're saying by saying that there's not enough evidence to reject it. There's not enough evidence to say it's wrong. Now, let's talk about this type 2 error. All it is type 1. Type 1 is associated with rejecting, and type 2 is associated with failing to reject. All that happens is you do your analysis, you do all of your calculations correctly. It's assuming that all of our math is done right. So when we say error, we don't mean you made a mathematical error. We're just saying that you did all of this analysis and you came up with an interpretation. But then when someone got a hold of the population, they found the opposite result to be true. So in our case, we said that it's possible that the yellow pods are 1/4. We failed to reject this claim. We failed to reject that the null hypothesis is the quarter. So if we fail to reject it, we're saying that it's possibly true. But then somebody went out and got the population of yellow pods, and they found out that we made a mistake, that it is in fact not a quarter. So if that were to happen, you would call that mistake a type 2 mistake. And all it means is that you failed to reject, but that was incorrect. You should have rejected. Now, it never happens right away. So you would do this study like in 2023, and then somebody in 2060 goes out and looks in the past and says, oh my, you were off. It's actually 1/5. And so when they would classify your study in the future, they would classify it as a type 2 kind of mistake. So this just refers to the kind of mistake you made. Essentially, you failed to reject and you shouldn't have, versus you rejected and you shouldn't have. That's all it is what happens in the future if somebody found out that you're erred, you had a bad sample, you didn't properly collect your data. Something happened that caused your numbers to give you a false result. And it's just how we classify them. But ultimately, that concludes just a big thing, understanding how to write that sentence. Let's do another. Moving on to number 2. And that's a good question. I don't know. I know they don't usually give one, but after you get so much experience using statistics, you can probably take the Microsoft Excel exam, given that you have a lot of experience with this, and then you can add that to your curriculum vitae. Okay. Starting at the bottom, we're going to test the claim that at most 10%, blah, 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 blah. That's the important part, right? You're talking about math here. So our claim is at most. We learned that before, back in test 2 and test 1. At most means you can go up to that number or less. It's the most you can go. So it means less than or equal to 10%. Talking about percentage, so that's a proportion. Now that we have our claim written down, is to claim the null statement or the alternative? Well, it has equality, and only one of them is allowed to have any kind of equality, and that's the null hypothesis. So the null hypothesis must be the claim because it has this equality part to it. That makes the alternative the complement, which is going to be greater than 10%. Okay, let's go grab our calculator, copy, paste it in somewhere. Obviously in the big boxes here. And there we go. And so what do we know? We know the claim was the null hypothesis. The amount in question was 10%. And we said the alternative was greater than, which means now I'm doing a right-tailed test, which means I only care about this right-tailed p-value. I don't care about the left one. I don't care about the 2 one. Okay. P hat. What was the sampled data, right? This is our sample measurement. Well, it says 9% of the sample. So there's your p hat. 9%. Sample size 1018. And poof, we have all of our calculations. And we have a very large p-value, 0.85623, which is okay. And so we're looking at a significance level of 0.1. So we'll say 0.1. And so, of course, is our p-value bigger or smaller than our significance? P-value in 1 decimal is about 0.8, 0.9, depending on how you look at it. And alpha is 0.1. Either way, it's definitely bigger than alpha. So we're going to fail to reject again. Fail to reject. Which, of course, means that if we do make a mistake, it would be classified as a type 2 error. Putting it together, our claim was the null hypothesis. We failed to reject. So this is your sentence. There is not sufficient evidence at the 0.1 significance level to reject the claim that at most 10% of adults say cloning of humans should be allowed, which means that we're saying that it's possibly true that no more than 10% think it's okay to clone humans. It appears to be true. If somebody in the future found out that was a mistake, we would classify the mistake as a type 2 mistake because you failed to reject and you shouldn't have. Reading through bottom to top, we're going to test the claim. The percentage of treated patients with flu symptoms is greater than 1.9%. So let's identify our claim. Our claim is the proportion is greater than 1.9%. All right. Does this claim have equality? Of course not. It's just greater than. So this claim then is the alternative statement. Because the alternative is the only one that has no equality. That means the null hypothesis is the proportion is less than or equal to 1.9%. Or if you prefer, you can simply say equal to 1.9%. Because again, for the null hypothesis, all that we really care about is what's the center. It's the alternative that's actually doing the calculation. And so often you'll see us just use equality for the null hypothesis regardless of the situation, where the alternative really depends on the inequality, so it matters which one for the alternative. And so technically, both of these are absolutely fine for the null hypothesis in terms of how you write it. Okay. Let's grab our calculator. Paste it somewhere. Oops. Copy it again. There we go. Okay. Which is why you'll never see me change the null hypothesis value of equal to, because it doesn't actually matter. It's the alternative that tells me which direction to look at. The value in question, 1.9%. What was the claim? The alternative was the claim. And we said the alternative was greater than. So we're doing a right tail test. So I only care about this right-tailed p-value. It's the only calculation I care about. Plug in what we need to know. If we read it carefully, we can see that 19 out of 878 had side effects. So there's my p-hat. 19 of them out of 878. A total of 878. And we now have all of our calculations. And the p-value is 0.0, not the p-value, the significance level, alpha is 0.01. So when comparing it, 0.28, 0.01, p-value is bigger, so again, we're going to fail to reject. But you'll notice this time our sentence is going to be different because our claim is not the null hypothesis this time. Our claim was the alternative. So our claim was the alternative, which is one of these two sentences, and we failed to reject. So now we're going to say this sentence. There is not sufficient evidence at the 0.01 significance level to support the claim that it is greater than 1.9%. There's not enough evidence to support the idea that more than 1.9% would get sick from this medicine. So we're suggesting that it's either equal to or smaller than, but there's not enough evidence to support the idea that it's bigger than. And there we go. I do want to point out that one other thing to notice, though, is when I talk about my rejection, I only ever talk about rejection of the null hypothesis. So even though the claim was with the alternative statement, when I wrote up my final conclusion, I talked about rejecting or not rejecting the null hypothesis. That's what we always talk to. We don't ever talk about rejecting or not rejecting the alternative. Why? Because the alternative is not equal to anything. It's just stating that it's somewhere smaller or somewhere bigger. But the null is equal to something. And so because it has a value, we can say whether that value should be denied or not denied, which is why we only talk about rejecting the null hypothesis. Excuse me.
I have a quick question.
Yes, go ahead.
So can we always assume that the null hypothesis will be true?
We assume it's true until we have evidence otherwise.
Okay, and we will never say that when we're terming this for our answers for our interpretations, we never say it's right. We have to use that exact termination.
Yeah, because we don't know if it's right. We only found a sample.
Okay.
So we just know that there's not enough evidence to say it's wrong.
Okay.
Now, if we have evidence to say it's wrong, we're going to say it's wrong. That's what happens when we get to a rejection statement. Good question. Starting down here, we're going to test the claim. Their portion have solar panels that's more than 9%. The claim is that the proportion is greater than 9%. That does not include equal to, so that must be the alternative statement, which means the null hypothesis, which is not part of the claim, must be its complement. And I can say less than or equal to, or I could just say equal to 9%. Let's go get our calculator. Let's copy it, jump into the question, paste it, and start filling in what we know. We said 9%. The alternative came from the claim, and it was greater than. So again, we're looking for a right-tailed test. So we found that 15 have solar panels out of 120. So our ratio here is 15. out of 120. A total amount of 120. We want a significance level of 0.10. That's our alpha. Notice in this case, we actually get to have a rejection finally. So the p-value is 0.09. Our significance level is 0.10. In this case, 9 is smaller than 10. So we finally have a smaller than case. That means we can say reject. We can say that we can deny the null hypothesis. We're simply saying the null hypothesis is wrong in favor of the alternative. So we're going to reject it and say the null hypothesis, we have enough evidence to say the null hypothesis is not a true statement. But what sentence do we say? Our claim was the alternative, and you rejected the null hypothesis. So here is our sentence. There is sufficient evidence at the 0.01 significance level to support our claim that more than 9% use solar panels in California. There's enough evidence to support the idea that more than 9% of homes use solar panels, which means we can reject the claim, the idea of less than or equal to. We can say this is simply not true. We got enough evidence to say the null hypothesis is wrong. But notice I don't state that the alternative is right. I just say that there's evidence to support it. There is sufficient evidence to support the claim that more than 9% have solar panels. I'm not saying it's right. There just seems to be evidence to support it. The only way you would actually know is if you went and did the population of homes in California. We can just say we either support or deny whatever claim we're working on. Claim is different than 42.3%. What do you think different means mathematically? Well, if it was the same, we would say equal to. And of course, same is opposite of different. So our claim here is that the proportion is not equal to 42.3%. So again, this is the alternative statement because there's no equal to. Its complement, though, if I wanted to know the null hypothesis, would be equal to. And we have a lot of the information we need now. But notice we're saying that it's different than 42.3%. We have no idea if it's more than or less than. That's why it's a two-tailed test. We have to check both sides. It could be more than, it could be less than. All we know is that we're saying that it's not 42.3. So copy, paste it, and we're saying that it's definitely going to be not equal to. The value in question is 42.3%, and the alternative is determined by the claim. And again, because it's not, we're doing a two-tailed test, and so we only care about the two-tailed p-value. So now we need to find our p-hat, our ratio, and we can see 280 out of 612 is our ratio, with 612 being the total amount. Now looking at our values, it's 0.08, and our significance level was 5% or 0.05. And so comparing 0.08 to 0.05, p-value is greater than alpha, so you would fail to reject. Because the p-value is not smaller than. One thing to point out, though, if you notice, had they had suspicion or some kind of intuition and they did a right tail test, they would have rejected. That's the cool thing about statistics, is that if you knew what the answer was up front, you could have had a whole different result. So because they had no idea which way it's going, they just said it's different. They had to meet a higher standard to get rejection. But had they said, I believe it's greater than, then of course they would have done a right tail test and they would have determined a rejection statement. But since they chose a two tail test based on their research parameters, they can't change it after the fact. That's cheating. They went off based on this information. They're going to fail to reject because that's the p-value that we care about. So putting it together, our alternative statement was our claim. We failed to reject the null hypothesis. And so this is what we say. There is not sufficient evidence at the 0.05 significance level to support the claim that it is different from 42.3%. There's not enough evidence to say that's wrong. So it's possible that it's correct. Claim at least 75%. So our claim is the proportion is at least, that means of course more than or equal to 75%. Because it has equality, that must be the null hypothesis, which means the alternative is simply its complement, which is less than. Let's go grab our calculator, copy, paste it somewhere, and start filling in. 75%, claim was the null, and we want less than. So of course, this means we're going to do a left-tailed test. So we care about that p-value right there. Okay. 138 out of 200. There's my ratio, my relative frequency. 200 total. And significance level is 0.05. And so if you notice, if I'm reading this, I started here and I only went up to here and I got to stop reading. So it really helps you to read bottom to top. You get to cut out all this other stuff that we didn't need to read and just save so much time. This test coming up is a lot of word problems. So you got to find ways to get through this a lot faster. But it's 0.05 because it tells us right here, significance level. And so looking at the left-tailed test, 0.2, 0.5, p-value is smaller than alpha, so we reject. We're going to reject the null hypothesis. And so, putting it together, the null hypothesis was our claim. We rejected the null hypothesis. And so here is your sentence. There is sufficient evidence at the 0.05 significance level to reject the claim that at least 75% of customers would avoid games that include ads. We're rejecting that claim. We're rejecting that at least, so 75% or more is right, which means that the answer is somewhere smaller than 75%. I don't know where it is. I just know it's somewhere less than 75% because I rejected the null hypothesis. I said the null hypothesis, because it's the claim, this statement is wrong. That means that it's wrong that at least 75% want it. So something less than 75% want ads in their games. Would avoid ads. Now, if it turned out that somebody went and found the population of gamers and found out the real answer, and it turns out we rejected by mistake, how would you classify that rejection? We'd call it a type 1. In other words, we said that we rejected the claim that at least 75% would avoid game ads, but it turns out that's true. We should not have rejected it if you made a type 1 mistake. Reading Bob at the top, you already see the claim right here. Proportion is 6% or less. The claim is the proportion is 6% or less. This has equality, so that must be the null hypothesis. So the alternative must be its complement. So those the claim wrote the first sentence, and so this is the alternative statement. Calculator, jump into the question, paste it somewhere. There we go. The null hypothesis came from the claim, 6%. The alternative was greater than, and so we're looking at a right-tailed test. All right, looking up here, if you're reading bottom to top, you're going to read until you get to your p-hat, and right there, 31 out of 350. Notice we don't have to read any higher. We have all the information we need now. Our significance level was 0.05. So if we look at our right-tailed p-value, it is 0.01 versus 0.05. P-value is less than alpha, so we reject. Reject. Putting it together, our claim was the null hypothesis. We reject it. So here's your sentence. There is sufficient evidence at the 0.05 significance level to reject the claim. The proportion of subjects who experience headaches is 6% or less. We're rejecting the claim that 6% or less would experience headaches. In other words, we're saying that it's more likely something more. We're rejecting the claim. We're saying that this seems to be wrong, and therefore we're saying that it appears that more than 6% get headaches. If I want to know how much more, I would use this calculation and create a confidence interval about it. I would take my p-hat of 0.808, roughly 8 or 9%, and construct a confidence interval and say some number in here is the true population proportion. And what usually happens in the real world is you do a hypothesis test. If you reject, you use your p-hat to create some kind of confidence interval, some lower and upper limit, and then you pick a nice number in there. Like maybe this thing went down to 8% and up to 10% or something like that. And so I would say, well, you know what? 9% is a good number in there. And so I would redo the whole test using 9% as my new center. And I would go and get a new sample, get new calculations, and see if I can fail to reject that number. If it does get rejected, then I do a new confidence interval, a new calculation. I keep doing it over and over again until I finally get a center that's not rejected. In this case, we're saying that it's not 6%, so we would need to go out and try to figure out what is that new center. And this obviously gives us intuition of where we should look. But it's only a sample, so we can't guarantee that that's actually the real center, which is why you make a confidence interval, because that should track the real center, right? All right, last question. Thanks for putting up with my scratchy voice. We've done this question before from a confidence interval perspective. Now we're going to do it according to a hypothesis test. So here, we're going to have to pick apart what this claim is, because it's not very black and white where we have a claim that says blank. The claim, though, is hidden in this sentence. That sentence right there I just highlighted, that's the claim. Throw it in the chat. What do you think this claim is saying from a proportions perspective? If you were to try to write that claim as a proportion statement, what would you write? I'll give you about 2 minutes to write something. I don't see any typing. Give you a hint. It involves this word called typical. When you think of the word typical, what are some good synonyms for typical? Especially from a mathematical perspective. In this case, when they say the word typical, what they're trying to say is most. The typical household simply means the majority of households. So we can assume that the typical household, in other words, most of our households, the mode would be okay. So in other words, we're talking about majority. Majority are safe, is what they're claiming. We can continue to assume that the typical household in Flint has safe water. If you look at all the houses, the majority are safe. So if we're going to say majority is defined as typical, can majority equal 0.5? No. Majority, if you recall, is defined as simply being greater than 0.5. Because if exactly 0.5 are poisonous and 0.5 aren't poisonous, then it's equally likely to have a poisonous house than you don't have a poisonous house. In which case, you can't say most houses are okay. So in this case, they're actually saying a majority, which means greater than 0.5, not equal to. And so this represents the claim. He's saying that the majority of houses are perfectly safe. And so that would be our alternative statement, which means the null by complement be less than or equal to. That the majority of houses are not safe, or at least not a majority of houses are safe because of the equality. All right, let's grab our calculator. That was a good guess, by the way. And so we said our claim was the alternative statement. The value is 0.5. And we're looking at a majority. So we're looking at a right-tailed test. So I only care about this right p-value. I get to ignore the other two. So you could just go in here and black them out so you don't see them. That way you don't write down the wrong one. Or, of course, you can just be careful. Either way. But now we need to find our p-hat. So p-hat, of course, you got to be careful about this now. He's talking about majority are safe. How do we define safe? Well, it's not safe for lead if you have more than 15. So if it's greater than 15, it's not safe. Which means if it's less than or equal to 15, then it's safe. And we're talking about this case from the perspective of the politician. From the politician's point of view, we want to know about the ratio of safe homes, because that's what his comment was about. The majority are safe out of total homes. So we don't necessarily care about the amount that are not safe, because he's only talking to the typical house. So we need to run through this thing and count how many safe homes there are. The cool thing is it might be easier to count the not safe homes and then just subtract off the total amount, because Excel can easily calculate when it's greater than or less than. And we're going to do that real quick and find out how many not safe homes there are. We can do that by saying equals count if this range, where our data is, comma, is, quote, greater than 15, quote. Otherwise, you can just manually calculate how many you want to do there. But what this is going to do is count how many numbers in that group are over 15. And there's 8 of them. And if you recall, we're told at the very top here, there are 71 total homes. So how many homes are in fact safe? Well, 71 minus 8 tells us that there are 63 safe homes. So we now know we have 63 out of 71 homes. There are 71 homes. And of course, we get this p-value. And you should remember from test 2 what that e minus 11 means. It simply means that we have 11 decimal moves. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3, 3. These two numbers are virtually the same thing. Oops, I forgot a 0, didn't I? Add another 0. There we go. These two numbers are the same thing. And so you can see that it's definitely very, very, very small. But looking at the significance level then, 0.01, we can reject the null hypothesis. And so putting it together, we would say we rejected the null hypothesis. The claim was the alternative statement, right? Our claim was the alternative statement. So we say there is sufficient evidence at the 0.01 significance level to support the claim, to support the politician's claim that the typical house is safe, that the vast majority of homes are safe. In fact, we found that 88% of the homes are safe. Now, obviously, I feel sorry for the 12% that don't live in a good area. But, you know, that kind of stuff. So be careful, because I see the chat comment about the 11%. They're not asking you for, we're not asking to make a comparison to the unsafe houses. The claim itself was talking to the number of houses that were safe. And 8 homes were not safe, which means 63 of them were safe. Exactly. And so 88% of the homes are safe in this community. So yes, the typical household, if you were to walk down the street and just pick a house randomly, you're more likely to find a house that's safe. That's what this is telling us. So the politician's not wrong in making that statement. But obviously, the 11% of people who are dying from lead poisoning have a problem with this kind of claim. And we'll get into that when we do a hypothesis test for means and look to see if the mean water level, or in this case, mean toxicity, is really bad. In other words, we're going to do this question again from a means perspective next week. All right, my friends, that was boot camp number 10, sorry. Boot camp number 10. There are 13 boot camps total, so we only have 3 more to do with me, and then you are forever done with me. Beyond my test reviews, of course.